Hello and welcome to our webinar about Hellixia, BayesiaLab's new subject matter assistant. My name is Stefan Conradi and I'm the managing partner of Bayesian USA and Bayesian Singapore. I'm delighted that so many of you have joined us today from all over the world. Right before the holidays is obviously very busy for everybody, so I really appreciate that you're making time for us today. Now, I'd like to extend a very special welcome to my friend and colleague, Dr. Lionel Schoof, who has dialed in from Bayesia's headquarters in France. Lionel is the CEO of Bayesian, and Hellixia is his brainchild. So there would be no one better qualified to tell us about this innovation in Bayesian network construction. Before we start, let me just mention that we have a Q&A panel where you can submit your questions. Depending on how much time we have, we'll answer them online or get back to you after the meeting. And now it's time for me to hand over the meeting controls to Lionel. Lionel, the virtual stage is yours.
Thank you very much, Stefan. Let me share my screen. All right, so thanks for joining this webinar. As Stefan said, this is going to be about Hellixia. So this is our new subject matter assistant that we created in February, so at the very beginning of the year. So it's now almost 10 months. And I already talked about it during the during the conference we did in March, but it was the very beginning. So since March, we added some new feature and we have increase the capabilities of Hellixia. And first of all, we also created a name for this feature. And so today, let me switch here. So now Hellixia is part of a menu. Before it was in tools. So now you have a menu called Hellixia. And as you can see, we have lots of features. And today I'm going to talk about the dimension elicitor. I'm going to talk about the embedding generator, the class description generator. We are going to talk about also causality, so with structural priors, and our brand new features that we created last week, the causal network generator. We are going to also see how we can generate images and then see how we can generate description to have, some nice name associated with the factors we create. And the last feature, which is also quite new because it's 1 month old. This is our analyzer of reports, right? So we are going to talk about these 8 different topics out of 13. And I'm going to start with, so I'm going to talk about 3 different topics here, 3 main topics. The first one is the dimension elicitors, keywords. So I'm going to focus on the keywords, create embeddings and see how these keywords are related. Then I'm going to switch to the expert knowledge elicitation topic. So talk again about Biki and see how we use Hellixia for helping us during our brainstorming session. So there is one part as a tool for the facilitator and the BBN modeler, just to get some kind of familiarization with the domain, because we are dealing with lots of different domains, so it's a super nice tool to understand the domain we are dealing with. And then we're going to see how we are also using it to help experts during the brainstorming session, right? And just mention again the way to reduce the complexity by using the independence of causal influence. And I'm going to conclude this webinar by talking about causal analysis. So I'm going to illustrate how we can automatically create a causal network on an example, the two-space stability failure. This is also the example I'm going to use in the second part. And conclude with a machine learning example with the famous visit example that we use since 20 years, but now where we can also find the causal relationships, right? So this is the schedule. So let's start with the first topic. So the keywords, focus on the keywords that we are using in the dimension elicitation. So I'm going to introduce this example by using embeddings and then unsupervised learning. But before going there, so this is here the wizard of the dimension elicitor. So as you can see, we have here 154 keywords that we have added, so that are available for your queries, right? So this is something that is hard-coded, if you want. So you don't have any way to add these keywords. So if you want some, you just drop us an email. But here you have, it's quite comprehensive, you're going to see. So 154 keywords. And before analyzing these keywords, I also want to use this slide to introduce or to talk about the completion models that are available now. So we have since 3 months, oh, not 3 months, 3 weeks. Now we have GPT-4 Turbo and 32K. So you have GPT-3, 5, and so on. So these are the usual OpenAI engine, if you want. We also are able to use, Azure engine, so the one you are defining by yourself if you want to have some more privacy. And I guess you are aware of now the GPT assistants that you can create by yourself. It's a kind of way to have the long chain, so the retrieval in this example at least. So here in green are my own GPT assistants. So I've created one for Hellixia. So this is one assistant that is dedicated to help you using Hellixia. And I have different examples here. So if you have created your own assistant, you can also directly use them here as a completion model. So it's very convenient, right? So for that, you just have to go to Preferences and go to Tools, select OpenAI. And so the first thing you have at the very top, this is the key of your API. So you have to use your own key, right? And then you have the second part is about the Azure part, so where you are defining your customized endpoint. So you see what you have to define the name, the URL, and the API key for this endpoint. And the last one is about the assistant. So you just, again, same thing, define a name, set the ID of the assistant, and use your API keys, right? So then with that, you can increase the list of completion models that are available for the analysis used by Hellixia, right? So let me start with, so it's a demo for illustrating how are related the keywords we are using in Hellixia. So here I already use this kind of way to analyze in March. So you have here, I'm going to open a database with just the keywords here. So I have my 154 columns, right? So it's a CSV file, 154 columns, one per keyword, and just 0 and 1. So it's just a trick for being able to create automatically these 154 variables. So it's 0, 1, but it can be A, B, or whatever. So just two different values to let BayesiaLab know that these are variables, right? So I have these variables that are going to be created. So you are used to these wizards, right? So here everything is discrete. So this is the reason why this is pinkish. And then once I have loaded this data set, I have obviously 154 nodes that have been created, right? And if I hover over the database icons you see at the lower right corner, you see that I have only 2 lines, 2 rows in my data set. So it's absolutely useless for machine learning, but I have my 154 nodes that have been automatically created, right? So now what I'm going to do is I'm going to create a data set with the embeddings of these nodes, right? So I've selected all the nodes, and then I go to Hellixia, and I will select embedding generators. So in this embedding generator, I can select to use the name of the node, the long name of the node, or the node comment, and/or, because it's not exclusive. And in this example, I just have the name, so I'm going to check this option. And here I'm gonna, so if you remember, I already presented this feature in March, but just to refresh your memory, perhaps. So an embedding, it's instead of just using an index for indicating what is the word here, what we do with embeddings is so first the words are tokenized. So a token is like 0.75 word in English, but let's focus on just the token. So instead of using an index for the token, so we are using this vector. So now in OpenAI, it's a vector of 1,536 dimension. So as you can see, you have the input is like 30,000 tokens. The output of this neural network is also 30,000 tokens. And the hidden layer contains 1,536 neurons, hidden neurons, if you want. And then, so they have learned, machine learned by using billions of documents, they have learned to predict when you see a token, what are the tokens that you can find on the left and on the right of this word, right? So with this learning, you have then the neural network is predicting what are the neighbors of these tokens, right? And then at the end of the day, you can think about these hidden neurons as like latent variables that indicate the concept. So for example, the token car, it's going to be connected on the right side with perhaps road, buses, accident, and what have you. And then if you have another token like bus, it's going to probably activate the same kind of neurons, right? And then because you have usually the same kind of neighbors, right? So thanks to that, you are also not just using a pure index for the token, but using a very rich vector, which contains a semantic associated with the token, right? So this is exactly what we use. So the embeddings is just the weight you can see on the left here from E1 to E1536. So it's a very nice way to represent the tokens, right? So then if we hover over the data set now, we are going to see that instead of 2 rows in our data set, we have 1,536 values that are associated with our node here. And if I double click on one of the nodes, or accelerator here, so I'm going to bring the node editor, I can see that this is a continuous value that goes from -0.68 to 0.22. So this is meaningless for us because this is just, weights associated with the link between the neurons here. And if we switch to curve in order to see the density function, we're going to see that this is like a Gaussian, a normal distribution with a mean of 0, more or less. And as you can see, it's we see the density of this activation. But again, this is not something that we can interpret. However, we can compare these activation level between these nodes, right? And this is what we do. We are going to do unsupervised learning to see how close the nodes are, how close the embeddings are. So it's going to be just based on association, right? And so for that, I'm using unsupervised learning. So given that I have this 154 dimension, I'm using just a maximum weight spanning tree to have something simple and fast. But even if we use something more complex, so like EQ, tableau, or so on, at the end of the day, with a discretization with 5 bins, you always end up with a tree. So which means no more than 1 parent per node here. So I'm using my maximum weight spanning tree. So I have this set of connections. So now I'm using what I call the 2-step radial layout plus symmetric layout, because if you just use directly the symmetric layout, sometimes you have some links that are, overlapping. So if you use first the radial layout and then the symmetric layout, so then in that case, you have a very clean representation of your graph, without overlapping links. And now, based on this graph, I'm going to use, the usual analysis to see what are the most important nodes and so on. So very nice interpretation with the node force. And here I'm using the mapping of this node force analysis. So something that we just added a few days ago is the font size is proportional to the force of the node. So this is something that allows you to have a better understanding of the mapping. So not only the size of the node, but also the font size, right? So we see here the strongest node, so is the keyword that has the highest force is threads, right? Which is connected with theme, profile, features, and so on. So we can see indeed the semantic connection between these nodes, member with individuals, drivers, player, agent, and so on. So you can already think about kind of concept behind that. So the reason why we have so many keywords is because it's a way to introduce some kind of I would say diversity in the answers given by Hellixia, because you can use causes, but you can also use drivers and so on. And thanks to that, you have different feedback, right, and answers. Okay. So this was the first example to illustrate how we can generate embeddings. And I use here the keywords to see the relationship between these different keywords. And we clearly see that this reflects the semantics associated with the nodes. Now I'm switching to the expert knowledge chapter, if you will. And I'm going to start with by introducing Becky really quick and see how we use Hellixia for helping the facilitator and the BBN modeler for understanding the domain. Then, so I'm going to create what we call a hierarchical semantic network. So it's going to be based on unsupervised learning and then variable clustering. And then I'm going to use this example to show how we can create automatically description associated with each factor. And then I'm going to switch to the second part of this example where I'm simulating a kind of brainstorming session. So to show when and how we use Hellixia when we have a group of experts to see how we can help them, and then quickly see how to create an ICI model. Right? So BK stands for Bayesian Expert Knowledge Elicitation Environment. So this is a web tool that is connected to BayesiaLab and that allows us to reduce the different biases that you can have during brainstorming sessions. And here it's just to illustrate the team. So obviously, when we do brainstorming with Becky, we have a team of experts, of subject matter experts, so can be engineers, doctors, scientists, and so on and so forth. We have a facilitator, so this is usually somebody from the company who knows the domain a little bit at least, and also knows a little bit of Bayesian networks. And he makes a bridge between the SMEs and the BBN expert modeler, right? And now, so the team has a new member, this is Hellixia. And Hellixia here, at least for the team made of the sub-team, made of the facilitator and the BBN experts, can be used for learning, for getting some information prior meeting the SMEs in order to understand the domain. Because we are doing lots of brainstorming sessions since 4 years in very different domains, and usually we don't know anything about these domains. So now that we have a Hellixia, we can real quickly understand or have some ideas about the domain, and then it's much easier to make or to help the experts to build the models, right? So I'm gonna illustrate here this feature by using. So I'm taking an example. This is a. Let's suppose that we are interested in, modeling or creating a model to understand why the stability of two space is failing. So we just want to be more familiar with this domain, and so I'm creating a new graph, and then I create a node that will be the support for my queries, right? So I'm creating a node that I'm calling two-space stability failure, right? And then I go to Hellixia and go to dimension elicitor, right? So again, first part, this is the set of keywords that are available. What kind of queries I am interested in? Sorry. So I have my 154 keywords. And now we also have groups of keywords. So this is a feature we introduced some months ago because when I was doing these semantic networks, I was always using some group of keywords together. And so instead of memorizing this group, we have created this group in BayesiaLab. So you can, depending on the theme, so because I'm using that for philosophy, for literature, for scientific things and so on. So each field has a different group of keywords that are useful. So you just create your keywords. And as you can see, I have a bunch. I have 36 different group of keywords right now. And so, for example, I'm going to use these four in this example here. So I have ancestor that is made of 5 different keywords: accelerator, catalyzer, causes, drivers, mechanism. So as you can see, it's like to find what are the main causes of a phenomenon, right? I have the characterization, the descendants, and the control. So this field, it was already there in March. So this is in order to restrict the number of responses, right? So if I uncheck it, then there is no restriction. I can exclude the duplicates and select my completion model. So again, I can use GPT-3.5, GPT-4, Azure, and you can also use your own GPT assistants, right? And at the end of the day, the new GPT assistant are a way to not to use a knowledge file, because knowledge file, this is something we had in March, because we had a tool outside BayesiaLab based on a database of documents and of chunk at the end of the day, and for each chunk was associated with embeddings, and based on the queries, we had some Python codes that were retrieving the chunks that were close to the query. So now I'm creating a text file, so the one we were using as a knowledge file. So now we can still do that, obviously, but the GPT assistant replace this feature more or less, right? So I don't think it's useful anymore, but then you still can use it, obviously. And if you have your GPT assistant, your own, you just use that for having a more specific context in your queries, right? You can also indicate a general context, right? Not market research, but market research would be better. And here it's not the domain. And then the subject of query. So again, can use a name of the node, the long name, or the node comment. And do not forget to hit the submit query here. So this button. So this is something even I'm forgetting sometimes. So you usually go directly to OK, and then you are prompted to select a query. So don't forget to hit this button, right? So once you submit your query, it's going to be right. So this is using the OpenAI API, trying to elicit the dimension. And then, as you can see, dynamically, you see the number of keywords that are created, or not keywords of dimension that are created based on your keywords, right? And here I have 69 different nodes that are created out of 116. Then I have, since I create a class per keyword, I have, so different colors, and I have these sticky notes associated with the group of nodes. I'm gonna hide these sticky notes just for clarity. And then, so I exclude this node because it's not useful anymore. And I'm going to learn a Bayesian network by using these different nodes. So again, I'm selecting all nodes, then create embeddings. The same thing I did with the keyword in the first example, but now I'm checking name and node comment because I just here I have the name of the node, but I have also a kind of long name or description of the node that is associated with the comment of the node, right? So the embeddings are going to take everything into account. So now I have a database made of 1,536 rows. And then I go and use my, not right now, my two-step layout, but instead I'm going to first use the maximum spanning tree, right? And now I'm going to use a layout. There is a mix in my label here. All right, so this is the semantic network that corresponds to the to space stability failure, right? So using the node force, just to have a quick understanding. So obviously the strongest node is about stability, the chemical stability. So we see exposure to light. We see that we have the humidity, we have the preservative, we have antioxidant, crystallization, and so on and so forth. Now, when you hover over a node in node force, you can see the comment that is associated with the node, right? So it's very convenient in this type of analysis because we have created lots of comments, right? And so this allows you to get more familiar with the domain. So we have a little bit of information about this. So we see that packaging has an impact, that the hardening and so on. The pH, right? And now, so I'm going to use variable clustering because the idea is to create a hierarchical Bayesian network. So it's those are the steps of what we call the probabilistic structural equation model, so PSEM. So I'm using now variable clustering to group nodes that are strongly correlated in this graph, and I end up with 12 factors. So same thing here. Now we have the font size that is proportional to the strength of the factors here. Sorry. Right. So the inadequate preservative is the strongest one here. When we hover over the node as usual, we have the list of the nodes that are associated with the cluster. And then when we validate, we have the class report. So two parts in this report. We have the first part is about, this is a list of the factors, and then so you have the factors and the nodes that are associated with the factor. And the second part of the report is the list of the nodes and the associated factor, right? And so now I'm going to click on the class editor in order to illustrate the features that allows you to generate names. So I'm selecting my 12 factors, then click on generate description. So I have the Hellixia class descriptor generator wizard, and I can choose, the length of the description. So from short to long, right? Let's suppose I'm between short and medium, I'm using GPT-4, and then go. So this will generate automatically a name. So you see the first factor, to space degradation and texture alteration issues, and so on and so forth. So you have that for the 12 factors. So let's suppose I want something a little bit shorter. So I'm selecting the 12 factors and then reduce. so the size. And then now the first factor is called two-space degradation phenomenon, right? So very convenient, because before, you had to ask the expert to think about a name, so to analyze what are the nodes that are associated with the factor, and then think about the domain and find a useful name, which is never easy and quite time consuming. So at the end of the day, since 15 years, people are just using the name of the strongest dimension to replace or to associate a name with the factor, right? So now it's much easier. And I'm going to export this description in a text file. So this way I'm going to be able to rename the factor with these descriptions, right? Now that I have my clusters of variables, I'm going to use multiple clustering to create one cluster. So I'm going to create, because here variable clustering is just a qualitative description of the cluster. So now for each factor, I'm going to create one hidden node. So I'm creating the hidden cause at the end of the day. And so using multiple clustering, we don't really care about these settings. And then it's like 12 data clustering that are automatically run here, plus so 12 different data clustering on each subset. So it's like dividing the data set in 12 sub data set, doing data clustering, and then at the end of the day we have a last final graph that is created. So this is the one here, and we have a summary of the learning that we don't read today, and we are gonna learn now the relationship between the factors, right? So we use taboo, we check, delete, and fix R just to keep the connection between the factors and the manifest. Otherwise, we're gonna lose these connections. And now we have then a hierarchical Bayesian network. So we go to data, associate dictionary of nodes for renaming the factors with the description we have created before. And now I'm going to use my two-step layout. So radial first, and then symmetric layout. And this is a representation in 2 dimensions of my hierarchical semantic network. So now let's go to the node force analysis. And we have the representation again with the font size that depends on the strength. Right? And after that, a little bit of layouting here. And then I'm gonna create or show you the mapping, the 2D mapping. So using the same kind of thing, but now, as you can see, we also introduce the font size here as a new metric. So you can define the size of the font based on the node force, the mean value, the entropy, and all the metrics that are available for the arc and for the node, right? So here I'm gonna use the node force. So at the end of the day, you have the same output as the node force here. And to conclude this, just want to show you the 3D mapping, just to really see that this is a hierarchical Bayesian network. And so this is a 3D representation of this network here, right? So the lower level, you have what we call the manifest variable. So these are the nodes that were directly created by Hellixia. And on the upper level, these big bubbles here, or represent indeed the factors that we have created. So the concept, a group of nodes, if you want, right? So this was for illustrating how we are using Hellixia for creating semantic networks, just to understand the domain, right? So now I'm switching to the brainstorming sessions, right? So we have the team here, and so usually when we start, we ask what are the main dimensions. So we have our target, and the facilitator asks this question, and the BBN expert modeler is sending the question to the Biki server, right? So this is sent to the Biki server. Every expert will receive, the question and then answer, and this will allow us to create automatically sticky notes, right? So this is now the Delphi approach for the elicitation of the dimensions. And now we have an additional expert, so we can also ask the same kind of question to Hellixia. So this allows us to check if we did not miss something. And I use already this feature in 3 or 4 sessions, and we always found extra dimensions that we missed, right? So let's see how this works. So we start again with a blank page. So now you have to imagine that we have a group of experts in the room. We create the node, so the target, if we will. So this is the node we are using for asking the question to the experts, right? So for finding what are the dimensions. So we use here, we don't care about the states, but we are going to use the comment field here, right? So we enter the question, what do you consider to be the 3 most important dimensions that impact to space stability failure? So this is the question that we ask. So here we ask for 3, but we can ask for 5. It really depends on the size of the group. And so we open the session, so the Biki session. So it's an interactive session. I'm the only expert in this example. And then we go to priority distribution, select one priority cell, and click on Biki elicitation. And then the expert that is connected to Biki, to the web interface, receives a question. So what do you consider to be the 3 most important dimensions impacting to space stability, right? So we just use the comment field here to indicate, okay, so for me, I don't know, pH is important, then temperature and packaging, right? So let's suppose that this is my expert knowledge with for 3, so just click on OK. And then, so this is sent to the server, and BayesiaLab will receive these dimensions. So we select the experts here in this wizard and check generate nodes from comments. So this automatically create a node where I have my 3 dimensions. And when you have a group of experts, as I use in the illustration on the left, then you have 1 sticky node per expert, and you have the list of all the dimensions. So obviously, you need to have the facilitator that will go through all these dimensions to see what are the different dimensions, because you can have perhaps 20 different dimensions, but some are very close and that you can merge. But for that, you need some expert knowledge, right? So we have then the list of experts, and now we can also use Hellixia for the same thing. So we just select the node, go to Hellixia, dimension elicitor. We select the keyword we want to use for that. So let's suppose I just use here ancestors, and I'm gonna just click also only 3 answers or 3 responses per query, and I submit the query. And with that, you see 12 answers, 12 dimensions that have been created with the comments associated with each dimension. And 12 out of 15, 12 are different, right? So now okay, which means that this will create a node. And let's suppose that I'm just focusing right now on catalyzer, right? So I'm gonna get rid of the sticky notes. So I'm just here isolating the nodes that belong to the class catalyzer, deleting the sticky notes here. And then let's suppose that I want to create a node that summarize these, or that will represent, you know, the latent variable associated with these three dimensions. So I'm creating this node like catalyzer. I'm adding links between the three parents and this node. And with that, I have 8 different distributions, assuming that pH, temperature, and moisture content are binary, which usually is not the case, but let's suppose this is just true and false here. So if I keep this means that I have 8 questions to ask to my experts, and it's usually like 1 or 2 minutes per question. So you can see that it's going to be quite time consuming. And not only time consuming, but also quite hard to understand and to be really coherent during these 8 different questions. So instead, we can use ICI. So for that, I'm selecting the 4 nodes, go to Tools, then select Independence of Causal Influence. And so in this wizard, you can choose what is the output. So all the other nodes are going to be the input, if you will. Then the combination function. So we have a list of combination function. So we can use, you know, the OR, AND, max, min, sum, and so on and so forth. So in this example, I'm just going to use an OR, right? And I'm going to use noisy OR. So for that, I just check the box a mechanistic local effect. I defining a prefix. So this is just to have a name that will start with C. So this is very useful when you have lots of different ICI models in your network. And this new option, condensed display, allow you to have a kind of automatic layout that is already done when you create your ICI. So this is very convenient during the session. So this is a new layout for that. And here, I'm just gonna change a little bit the rendering of the nodes. So by changing the label position to bottom to top, right? And so in this kind of approach with ICI, you just have to define to ask the expert, what is the local effect of each node, right? So what is the local effect of pH, assuming that temperature and moisture do not have any influence, right? Or are in their neutral state. So instead of 8 questions, in that case, you just have 3. So we have the neutral state here. So if pH is false, then there is no effect. And here, this is the noisy effect that we are going to elicit. So I go to Wiki, and as you can see, there is a question. What is the independent local effect of pH fluctuation on catalyzer? Well, so we have the distribution to set, so here 75, and this is a new way to specify the confidence level now. So you have a slider where you go from clueless 0% to certain 100% of confidence, right? This is sent to Wiki. BayesiaLab is listening and receive the priority distribution. So you have to imagine that we have 5 to 10 or 15 experts that are doing the exact same thing, and then you are capturing all their probabilities. You have their confidence level. We are using this confidence level for computing the kind of weighted average of the distribution, the consensus, right? So now we have this ICI. So I just want to show you one network that we did with L'Oréal a few months ago. So it's a Bayesian network that we have designed in order to do some kind of triage among the different projects that we have with them. So it's a network we have created. We were 7 experts, if I remember well. And this was the first time I was at the same time the BBN modeler and also an SME. And so we spent 2 days building this model, just really to find what are the key dimensions that allows you to predict the success of a brainstorming session. So at the end of the day, given that we never had any failure in this BBN approach, so the idea was more perhaps to focus on the condition of the project. So because success is not, we don't have really lots of uncertainty, but the easiness here, it's probably more important. So this is what we call here the project condition. And because sometimes, it can be hard when you have, for example, the spacing of the session is very long, so this is not easy to do when you have experts that are not there all the time and so on. So as you can see in this network, we have a block of variables that are used to describe the workshop itself. So session format, spacing of the session, the experience of the facilitator on the BBN modeler. Then in green, you have everything that is related to the experts. So how many experts per domain? Are they motivated? Is there any conflict of interest, the size of the group, and the constant presence of the experts? And we have also the pre-work part. So did we do a training? Did we interview the experts? Do we have a clearly defined question? And this is the most important dimension at the end of the day. And also, are the experts anticipating the way to exploit this domain? So these are really the 2 key questions at the end of the day in the defining the quality of the model. So as you can see here, it's a model that is using like 17 or 18 inputs, and we have used noisy OR, right? So, or noisy M, sorry. As you can see, the orange nodes here are all M's, and we have the mechanistic local effect to define the noise, right? So we have then created a simulator, right? So this is the simulator. So we publish the simulator. So you should see, so this is a public simulator. So you have the project conditions, the model quality. So if we say that the question is not clearly defined, you can see that the quality of the model is greatly impacted, right? But if it's clearly defined, it's much better. Are we anticipating the model operation? Yes. So you can use this for really trying to estimate the quality of the model that you are going to generate via the brainstorming session, right? And this is also a way to find what are the really the drivers. So if you want to increase the chances to have a success, see what are the dimensions. So decrease the spacing of the session, increase the number of experts, and so on and so forth. And so the last topic is about now causal analysis. And I have, again, 2 subparts here. So I'm going to still use a 2-spaced example for the first part, and then switch to the Visit Asia example, right? So the first part is 100% based on Hellixia, so no machine learning. And the second part is based on machine learning and Hellixia. So let's suppose that I'm creating my node here, 2-space stability failure. And I go to Hellixia and I select now the new feature, causal network generator. I'm, again, as usual, select the completion model, right? So GPT-4, Azure, or your GPT assistant. So here I don't have any GPT assistant for this domain, so I just use GPT-4. I'm using just a node name because I don't have any comments, and I can also create classes because we can obviously use that incrementally and create causal network on causal network on causal network, right? So classes will allow you to quickly identify what was the request, right? So here, obviously, it's a video because this is a very complex task. So it lasts at least 2 minutes, right? So I recorded that just to not to have any problem with timeout and so on. And then we have this network, right? So as you can see here, it's not just the elicitation of the dimension, but you already have the entire graph, right? So I'm using the genetic grid layout algorithm for that. So the first one is a top-down. You click on the red button to stop the algorithm, and perhaps the bottom up is better in that case. So I'm using the bottom up here. And as you can see, I have the two-space stability failure that is explained by 4 direct causes: microbial contamination, packaging interaction, chemical instability, physical instability. And then you have some levels. So microbial is defined by the pH level, by the preservative, and pH level is also impacting the chemical instability. And so you have all this information in your network. So we have, as when we do dimension elicitation, we have the name of the node, but also in the comment, we have a long description of this dimension, right? So here, this is a substances added to the two-space to inhibit microbial growth and extend shelf life. And we have also a comment associated with the causal relationship. So you have the causal link and the explanation of this causal relationship, right? So here the preservative are used to prevent microbial contamination that can lead to space instability, right? So for each node, comment, and each relationship, a description of the causal relationship. So now I'm gonna select all nodes and switch to a visualization with badges, which can be very useful in that case. So here I'm selecting all nodes and just to define a fixed size. So this allows to have a very clear representation of your causal network with badges, right? So now you have the name and you have a clear description of each dimension without having to hover over the node. And then I can also display the relationship or the explanation of the relationship. So this is in blue. So you have one comment per link. So we still do not have any way to conveniently be able to read everything on the link because we have lots of information, but we need to work on that, right? But at least you can go through link by link and read the explanation. And you can also create a report of comments. So if you go to network reports comments, then we can generate a report, HTML report that will summarize all the comments that have been generated here. So you have the comments associated with the nodes and the description of the causal relationships. Okay. So this is another network. So because it's a so long process that, first of all, it's not, even though we have a temperature that is fixed and we have a seed, still, if you ask twice the same question, you are not going to have the same result, right? Because probably some tokens have the same probabilities. And so you have some variability here, which at the end of the day, it's not that bad, right? And here, this network is another one where instead of two-space stability failure, I ask for just two-space stability. So this is like the reverse. And then you have a slightly different network, which is also very interesting indeed. So two ways. So what is the causal networks that explain instability and what is the one that explains stability, if you will. Right? And let's conclude with the machine learning example. So as I said, I'm going to use the VisitAsia example, which is our basic machine learning example since 20 years. So we open the text file that describe virtual patients. So we have in this example, so it's based on lung diseases. So we have smoker, so we have 8 variables here: smoker, cancer, age, tuberculosis, VisitAsia, X-ray, bronchitis, and dyspnea. I have 25,000 patients here, and I'm gonna read this data set and create, by using machine learning, the network that represents this, the joint probability distribution that is sampled by with these 25,000 patients, right? So I just go to learning, unsupervised structural learning. I'm using EQ, and I find this network. So a little bit of layout, then some kind of manual layouting here. And we can see that, so for those who know this network, it's the skeleton is perfect, but we have some orientations that are not correct. So for example, you see that we have cancer that is directed to age, which obviously does not make sense, but BayesiaLab cannot know that, right? Because these connections are what we call equivalent. So there is a way in BayesiaLab to visualize what we call the essential graph, right? So we just go to visual graph and then equivalent classes. And as you can see, this allows you to highlight connections that can be set, or the relationships that can be set in both directions and that are, from a probabilistic point of view, absolutely equivalent. So for example, here's a connection between smoker and bronchitis. There is no way to know if it's smoker bronchitis or bronchitis smoker, right? Just by analyzing data. Smoker cancer, smoker age smoker, and so on. Same thing. Visit Asia, tuberculosis, same thing. So if you set the orientation in one direction or in the other one, you're going to have the exact same joint probability distribution. So by using usual or basic machine learning algorithm, no way to find the correct orientation. So what we usually do is either you have some kind of temporal information that you can use, or you have some expert knowledge. And obviously, you know that this is not smoker that has an impact on age, but age that can have an impact on smoker. And smoker has an impact on cancer, not the other way around. But again, just by using data, no way to find this. So here what we do, instead of calling an expert, we are going to call Hellixia. And so we select all arcs, and then we go to causal structural prior. So this just is, we by selecting the connection here, we just send these relationships, these bivariate relationship, to Hellixia, and Hellixia will analyze the causal relationship, if any, between these couple of nodes. So we can again specify a general context. And this generates what we call the structural prior, right? And here we have the list. So you have the first one, visit Asia, tuberculosis. Yes, this is traveling to Asia may increase exposure to tuberculosis. And you have a new column, check here, that indicates if the orientation that has been found, the causal orientation, is something that you already have in your network. So when you have this red box here, or red cross, this means that this is the other way around in your network, right? So we have three kind of mistakes in our network, right? But again, there's no way for BayesiaLab to find the correct direction here. And for example, visit Asia, tuberculosis, it's correct, but just it's by chance, right? So now that we have the structural prior, we can use them for machine learning. So we are gonna use unsupervised learning by taking into account the structural prior. And as you can see now, EQ, Taboo EQ, Soplek are not available anymore. So this is something, so we had lots of feedback when we released version 11. So now EQ is not available, or all the EQ algorithms are not available when there are some options that make that AB and BA, or the two connections, are not equivalent anymore. So it can be due to, so structural prior, it can be due to constraint, it can be due to all these options that make the relationship not equivalent any longer, right? So now in that case, we have to use Taboo or Taboo order. So I'm using Taboo, and we have our causal network, right? So now everything has a correct direction, causal direction, right? So I can, now that I have everything in the correct orientation, I can store the explanation on arcs. And set a visualization based on monitors. And now I'm gonna use this example to illustrate the tool that allows us to analyze the relationship report. So for that, I'm going to first check, you know, the order of the states, because here everything has been created automatically by loading the data set. So you see the state visit Asia is, or the states are no, yes. So everything is no, yes. So far so good. But for X-ray, it's abnormal, normal. So if we want to keep the same logic, it should be normal, abnormal. So we need to have the kind of neutral state at the first one, and the one that corresponds to a kind of failure, the second one. So I'm going to change this just to keep the same logic here, right? And same thing for age. You see it's here. We need to change the order for having young adult, adult, and senior. So now everything is coherent. And then we can go through the analysis, report, and relationship analysis. So this report is analyze the strengths of the connection between the nodes, right? So you have, for each relationship, you have the mutual information, the callback library divergence, and so on and so forth. And you have a second part of the report that indicates the force of the nodes, right? And now we can call the report analyzer of Hellixia to create a kind of a story based on these relationships. So I just indicate here the context, so lung diseases. And then Hellixia will analyze this relationship and create this report. Right? So you have a kind of story here about this domain. So with two main parts, the first one is focusing on the force of the nodes. So here we know that this is bronchitis and dyspnea. And then the second part is based on the relationship, so the relationship between the variables, right? So you have the primary relationship between bronchitis and dyspnea, you have the diagnostic indicator with X-ray, you have the behavioral and demographic influences, and you have, at the end of the day, the international travel and disease risk that is just based on the relationship between visit Asia and tuberculosis. Then we can save this report in a node. Right? And now, last example is to see how to use DALL-E to create icons. So now that we have DALL-E 3, is much better than it was before with DALL-E 2. So you're going to see that now it's quite cool. Using DALL-E 3 allows you to get this kind of icon. So obviously, the speed has been increased here because you need at least 1 minute to generate these images, but still it's quite impressive. And then you have this nice illustrative causal Bayesian networks that have been machine learned, right? So just to conclude, you have an extensive user guide on the website. So it's under Hellixia user guide, and lots of examples. So you have different types of example, but it's so convenient to create example with that. So you have philosophical minutes, you have a section dedicated to philosophy, another one to literature, cinema, song lyrics, causal semantic network, and so on. So lots of networks here, and you have the workflow that is described step by step for all these examples. So if you want to find some inspiration, you can go through this website.
Right. Lionel, thank you very much for your fascinating presentation. It is so exciting to see how ChatGPT and large language models can be leveraged for developing Bayesian network models. I really think that this technology will transform how many of us work with Bayesian networks. Let me conclude our event with a quick outlook on 2024. On April 11 and 12th, of 2024, we will be hosting our semi-annual conference. And for the first time, our community will meet again in person. I think it will be a great opportunity to learn from practitioners about practical applications of BayesiaLab and Hellixia, of course. Our conference venue will be the Graduate Hotel on the campus of the University of Cincinnati. And in the context of the conference, Lionel will also teach the highly acclaimed introductory and advanced courses. So I'm really excited to reconnect with all our friends and clients for the first time since before the pandemic started. So please mark your calendars and start making your travel plans. The conference registration is already open. This concludes today's webinar. I'd like to thank Lionel for his brilliant talk, and I also want to thank you for participating in today's event. On behalf of our entire team at Bayesian, I'd like to wish you happy holidays and Merry Christmas. We hope to see you all again in 2024.